Good day and welcome back. In this video we will begin our discussion of Green's theorem, which is a fantastic result relating together double integrals and line integrals, two of these recent large topics we've been discussing. Before I'm able to state Green's theorem though, I will first need to introduce a bit of terminology, what it means for a simple closed curve to have a positive orientation, a bit to unpackage there, along with a quick reminder. So let me begin with the reminder. If we have a two-dimensional vector field, so if we think f is given by a first component p and a second component function q, then the line integral over the vector field f can be expressed as the line integral of p dx plus q dy. And whenever it is convenient, we can interchange the two notations. The statement of Green's theorem requires a simple closed curve that has a positive orientation. So the first thing that I believe is new here is this idea of what does it mean to have a simple closed curve. The closed part is simple. It starts and finishes at the same point. The simple part means that the curve does not intersect itself. So an example of a simple closed curve would be a loop that starts and finishes in the same point. Something which is not simple would be a curve that intersects itself. So if we had a closed curve that looks kind of similar to, say, a figure 8, that would be not simple. And the reason that it is not simple is because of the point the curve intersects with itself. Now the positive orientation portion refers to a single counterclockwise traversal of the curve. That is, when we go around this simple closed curve, we go around exactly one time in the counterclockwise direction. And note, as you travel around this curve one time in the counterclockwise direction, you will enclose a region to your left. So if I imagine walking along the curve, that green arrow is pointing to my left. That's indicating a region, let's call it D, which is enclosed by the positive orientation of a simple closed curve, C. And we now have everything necessary to state Green's theorem. And Green's theorem tells us the following. If we have C, a positively oriented, simple closed curve that bounds a region D. Think the picture above. Then the line integral over that boundary curve of the form p dx plus q dy is equal to the double integral over the region D of dq dx minus dp dy. So the idea is that we could start off with, say, a line integral that may be difficult to evaluate and express it in terms of a simpler double integral. Or even, as we'll see later on, vice versa, we might start off with a double integral and turn it into a line integral. And the formula that we have here is the big takeaway for this section, Green's theorem. But note, we always need those precise hypotheses. C must be a positively oriented, simple closed curve. And note, the integral that we have is really the line integral over a vector field. And that line integral over a vector field calculates work. So this is very much related to recent topics of interest. Before going on to an example, I would like to note that even though the statement of Green's theorem applies to a single simple closed curve with a positive orientation, it also works when you have a region bounded by two simple closed curves. That is, and this is something we will encounter in future examples, but it's worth mentioning at this point as well just to kind of plant the seed. And if I wanted to illustrate this as simply as possible, I could do so with an annular type region. So note, two simple closed curves. We have a simple closed curve on the outside, a simple closed curve on the inside. And note I haven't put any stipulations in terms of the orientation of the curve. Now, how would we have to travel around these curves in order to enclose some region D that will always be enclosed to our left? If I start at a point and I imagine I travel around in this positive orientation, I will be enclosing some region to my left. So just imagine what direction is to your left as you're traveling around this curve. So we travel all the way around the outside curve with that positive orientation. Then I travel along this dashed line to the inside curve. And when I get to the inside curve, I'm actually going to go around it in the opposite direction because I want to enclose that region to my left. And once we travel around to the point where we hit that inside curve, then we go back to the outside curve. And note the fact that we have traversed this connecting curve twice, that contribution in a sense cancels off. So nothing to really worry too much about at this point, but I just want to indicate that what intuitively makes sense is true. That is, we can apply Green's theorem to this region bounded between two simple closed curves. And for now, we'll just kind of put a pin in this and revisit it at a future time. Let's finish up our introduction into Green's theorem by looking at an example. And a typical example involves a line integral to evaluate, and that line integral can be given as it is here, or it could maybe be describing the work done by a vector field, where in this case C is the positively oriented rectangle with vertices at 0, 0, 5, 0, 5, 2, and 0, 2. So 5 in the x direction, 2 in the y. So we have a rectangle indicated in blue, and it has a positive orientation. Now the starting point is this line integral. And in order to evaluate this line integral, if we go back to our previous techniques, which we certainly could do, you would have to take the rectangle, break it up into its 4 individual sides, evaluate the line integral on each side individually, and then combine those results together. And I agree, that does not sound like the most fun or even quickest possible approach. Instead, what we are going to do is apply Green's theorem. Note, as you travel around the curve C, you enclose this rectangular region to your left. And Green's theorem tells us, and whenever we apply Green's theorem, we will always indicate it by putting a small gt over the equal sign, much like we did with the fundamental theorem of line integrals. And Green's theorem implies that this would be the double integral over that rectangular region D, and we'll be integrating dq dx minus dp dy. And note, p is the quantity paired up with the dx, q is the quantity paired up with the dy. And we do have to be careful to make sure we pick our quantities appropriately. We do not always need to have the order something dx plus something dy. So it's not that p is always first and q is always second. But remember your alphabet, x, y, p, q. So we have the double integral over d of dq dx, so the partial with respect to x of x squared sine y, minus dp dy, the partial with respect to y of cosine y. And if we evaluate these partials, we would have 2x sine of y minus a minus, making it a plus, sine of y. So what was originally maybe a difficult looking line integral, at least in terms of the process and efficiency of evaluating, has now turned into an extremely reasonable double integral. In fact, it's the ideal scenario. We're integrating over a rectangle, and our integrand separates into a function of y times a function of x. So it's even the ideal scenario for us to evaluate. And as the order is irrelevant, I'll say dx dy. X varies from 0 to 5. Y varies from 0 to 2. And taking this another step or two to quickly evaluate it, we have the integral from 0 to 2 of sine multiplied by the integral from 0 to 5 of 2x plus 1. The antiderivative of sine is minus cosine. Antiderivative of 2x plus 1 is x squared plus x. And when we evaluate, we would have minus cosine 2 minus a minus cosine 0, which is 1, times 25 plus 5, which is 30. And as stated previously, this line integral, which would have been previously time-consuming or difficult to evaluate, has now become much simpler via Green's theorem as a double integral. We will continue this investigation in the next video, so stay tuned and take care.